What's up, everybody? Welcome to Geology. So, in the little intro sheet there for this segment, I asked you to consider why is the shoreline for Oswego so smooth? Now, I'm not saying there's not like this big Mexico Bay right here, this point where 9 Mile is, or any of that, but generally, it's pretty smooth. Like here at Sodus, why doesn't the shoreline come in and follow this? Or, I mean, they're all over the place out here. Why has sediment filled that in and made, when you zoom out, the shoreline of Lake Ontario so smooth? And then in places, and in fact, it's the one that I put on there, those have like kind of backfilled and filled in. This is the swamp over near Sterling Nature Center up here, the bluffs up here, if you've ever been there. And then you can walk the beach between the two that's completely filled in with sediment, but there is what might have been lower than lake level, but now is kind of backfilled and gotten swampy and filling in. So why doesn't the shoreline follow these kind of jagged curves? So there's got to be more than just waves in and waves out. There's got to be other processes, and that's what we're going to try to figure out is some of that, along with barrier islands. We don't get those on Lake Ontario. We get them down here. And in fact, some of you, I'm probably going to be talking about where you live, down through Jersey and really down this whole Atlantic coast. The biggest, example would be this one in North Carolina. That the name is eluding me all of a sudden. What do they call that? It'll pop back in my head. And then I know your book refers to Folly Beach in South Carolina. So we'll look at that a little bit as well. In fact, that's what is on the notes right here. So what like hazards are associated with it? Where have humans moved too close? Where have we altered the nature of what the cross section of a barrier island should be? How do waves and all this? We got a lot to do, right? So if we had a happy barrier island, so I would label that as a barrier island, right? And we can zoom in on that in Google Earth. I guess I turned off borders and labels. It'll be harder for me to find it. It's right over here. So where have we taken what might be a natural environment with very dynamic? This is, I mean, on the Notion, with a lot of different weather events that are going to be happening, a lot of different currents. These are supposed to be very, I don't want to say supposed to, that's not the right word, but these just are very dynamic environments where through the years, dunes will grow and get destroyed, erosion, deposition, different balances, and maybe they migrate up and down the shore as well. Our problem, and this is what I tried to think about with that blurb saying, hey, if you showed up at low tide and built a house, you would soon find out it was a bad idea, right? Over what kind of timescales are we willing to accept very dynamic situations changing, right? And if you were somebody that bought property on one of these things, that time scale is going to be a lot longer, right, than what might naturally be taking place. And again, I know some of you are going to be from areas like this on Long Island, and I'm not saying, I guess I don't know what I'm trying to say, right? I'm not saying you're a bad person, but I'm saying that we have to like understand the nature of the earth if we're going to inhabit it, right? So what have we done in these areas is, where's my notes? Is take what might have been an area with all of the different regions that actually would be more stable if we had let it do its thing, and oftentimes just flatten the entire thing so that it's convenient for building houses and cars and communities, and get rid of vegetation, get rid of dunes that absorb some of the impact of this, and then alter beaches a lot depending on how often they get used. And then what happens back here on the bay side too. I know this is Gulf of Mexico, but it's the same basic cross section wherever you are. So let's dig into waves a little bit and think about how these work, and get into what there will be a couple questions about this on the quiz. So some definitions we're going to need. One wavelength would be the distance from one crest to the next crest, or equally one trough to the next trough. Height or amplitude, and then period would be how much time passes as they go. Now, if you've ever goofed around in water, especially deep water, once you get out past the breakers a little bit, if you're in the waves, or you throw a tennis ball or something out there for a dog. Out here and past the breaker zone, deeper than the breaker zone, you get caught in these orbitals. And what a wave is really energy moving forward, not water moving forward. If water, like in this hump of the wave, were moving forward, there would have to be some kind of plane that it's slipping across, and that would look really bizarre. That's not what it looks like. It's energy, and one water molecule itself, if you could like tag one and look at it, you would see moving in these orbitals. And they continue down and get smaller and smaller and smaller, down to a depth, excuse me, that's equal to about half the wavelength. So it's a function of wavelength, really more than heights. Deeper than that, which this diagram doesn't go, if this diagram went out a little deeper, the orbitals aren't contacting the ground. The waves are just, the wave energy is moving towards the shore. Again, water molecules are not. But once it starts to hit the ground, which again, about, says right there, about half the wavelength, some interesting things happen. Because now it's going to do a couple things. It's going to slow down as it's like dragging on the bottom. The amplitude, the height will start to get bigger, and it starts to drag. They get closer and closer together because they're slowing, and eventually will begin to break. And it's if you take some time, and I know that we're almost at the end of the term here, but if I've infected your brain at all with this, if you are at Oswego and you just watch Lake Ontario on different days with different kinds of waves, you can kind of figure out where the subsurface is more shallow and or deeper based on where the waves are breaking. And the point that's kind of off the health center, which I guess I should just bring up rather than having you envision, if you can check that out one day. So right around here, in fact, geez, you can almost see it in Google Earth. There's some places where there's some shallow, like flat rocks out here. So waves are breaking on that, but not everywhere else. And then once they get close to the shore, they do as well. And in fact, this shows us the next thing we want to see: wave refraction. No matter what, and this is almost, I don't know, it's crazy. The first time I heard this, and even though I was into science, I was like, no way that happens, but it does, and you can observe it on this curved shoreline. By the time that the waves hit the shoreline, they're parallel with the shore. You see here, you can see it's like parallel with the shore here, parallel with the shore here, parallel with the shore here. Well, if the wind's coming out of the northwest, it looks like, well, what's the deal with how it all of a sudden, when you get here, it's parallel? It's due to what we're talking about here, that once they begin to drag, they also refract. Now, wave refraction, general backup, is a general science term. Anytime, it can be a light wave, like if you put a straw into a glass of water and the straw looks like it's bent or broken, that's light refracting. It's just a term for when waves bend. So here, waves of energy in a body of water do the same thing. That when these orbitals detect the bottom at the depth of about a half a wavelength, they bend, so that they call this the normal, so that ends up perpendicular to shore, whereas the crests end up parallel to shore. And that is going to give you not only that, right, but it also in places will concentrate wave energy. Let's take a quick field trip to Newport, just because I know these beaches, because I've used them in examples like this in the past. In fact, I think I have on tests. So here's Newport, Rhode Island. And here's really, it's just a very typical, very easy diagram or area that really resembles like textbook how this works. And as a kid, we did some trips out here, family trips out here, and it leads to some pretty good like little surfing spots and boarding spots. And that is that as waves come in off the ocean and they bend, when they detect the ground, they get concentrated on these headlands. So if it juts out, it pulls all the energy in. It looks like I don't have my little drawing tools, but if you follow the cursor, it would come in and then bend in towards that. Straight on, it would pretty much go straight on. Over here, it would bend in towards that. That means this area is really getting like pummeled by the wave energy. And as a result, there's not really going to be any sediment just chilling out there. These are all very rocky cliffs. It's too high of energy environment for small sediment like sand, for what makes up beaches, pebbles and sand, to make it. Where do pebbles and sand end up? In the lower energy environment. So if you go to the bay part of it, energy gets refracted away to the rocky spots. So that means over here, it's calmer. And that's where you're going to get your deposition of sand. And that should be just pretty much what the diagram shows us here. Rocky headlands in sandy bays. High energy, low energy. Which I think we talked about back when we did rivers, right? If energy speeds up, if water speeds up and it has more energy, it's capable of carrying larger particles. That's what erosion is. If it slows down, it's going to drop those particles off. That's what deposition is. That's going to be what builds your base. Yeah. No, that's not it. If it were that simple, it would be, right? What else is going on? There's also this idea of longshore currents. And this is going to be what really fills in these bays. So let's go to, there's some seawalls and stuff here. In fact, this one's interesting because we had high water in, 17 and 19? This one got kind of wiped out. But maybe we can go back in time. See what happens. Yeah. All right. So this is, if you haven't been to Fairhaven, Little Sodas Bay is over on this side. This is called Blind Sodas Bay. That was completely intact. So what's happening here? This is a function of longshore currents, which is the current in the water, and longshore drift, which is the sediment that gets drawn along with that current. So waves coming in and out at an angle end up, and it's in the notes here, it's not just a straight up in and out. And this is going to be why the shoreline of Lake Ontario got so nice and smooth, because it's not just an in, out situation. And in fact, if you've goofed around on the beach as a kid, this is like the scenario. This always happens, right? Your parents are here, you go in the water, you're playing, and all of a sudden you realize you've like drifted down shore. Not in like a minute. This isn't enough to like sit and just go floating away. But after you're out there for 10, 15 minutes, you've moved down by like 10, 20 feet, right? Because you're slowly, every time one comes in and one comes out, the resultant of these different forces shoves you down the longshore current a little bit. And as that happens, and it carries sediment, it drops it along. Now, again, the high water came in 17 and 19 and wiped out that whole thing. In other places, it's more stable. Here's at Fairhaven. And we'll go up to, I grew up goofing around at this beach up here on Sandy Pond. This is an example of a spit going way out. And again, why isn't the shoreline of Lake Ontario like this? Well, because the longshore currents that carried sand, a lot of which comes from the bluffs down there. You notice that the on campus, the beaches there are all rocky. Where's all the sand? It's a really high energy there, and that gets carried up to this end of the lake, and it gives us this spit. And they're pretty tall dunes through here, especially now that they've worked to restore them a bit. When I was a kid in like the 80s, these got a lot more beat up. People would like drive trucks right up through here. It was a little looser and crazier then, right? So they've done a good job through like volunteering and just raising awareness and building decks and directing traffic, of rebuilding some of the dune grass through here and making the dunes start to grow back again. But again, dynamic environment, constantly changing. When again, this is a family place. When my grandpa had it in the well before I was born, there was a channel, and you can still see this on maps, topographic maps, down here somewhere. Now the channel between the two is way up here, and it's if you check out the people that like to jam their boats up onto the sides of this here, they're constantly trying to dredge this, and it's constantly filling in with sand. And they're again, it's a dynamic environment. What are you going to do? This is not something that we can expect to be stable. There's constant arguments with it, which get frustrating at times with the varying degrees to which some of us understand how longshore drift, how spits, and all of this work. Anyway, I don't want to get too down that rabbit hole. So what are some things that humans can do to try to control this? So a groin is a like a hard feature that you'll stick out into the water to say like, hey, here's my premise. If slowing down water decreases its energy, it will deposit its sediment. And that's a great idea. So it does. The problem is that then as the drift comes and whips around this, it ends up eating away at this even more than it was before. So you go from what might have been like a flat beach to, yes, gaining beach here, but then losing beach here. So then you build another groin. And then, right? It goes on and on. You can see that to some degree at Selkirk. But there's one in Chicago where it really stands out. So the longshore current is coming from the bottom of the screen going up towards the top, and you can see that the sediment on this side is more filled in, and on the down current side is more like eaten away. And same thing over here. It's really pronounced in Chicago. And in fact, how about this? I won't say which direction it's coming from. Maybe I'll try to pop that question on the quiz. So look at that Selkirk one. Rewind this video a couple seconds there if you want to like review it. But what would be the deal at this beach? Here we go. So there's some groins built out. You can see where the sediment is being deposited and eroded. So you tell me, quiz time, where's the longshore currents coming from? We'll see how that goes. So yeah, the basic features. This I just threw this in there. Like we've pretty much talked about a lot of these. Between a spit, a barrier island is like disconnected. These you get out west, you tend not to see these where we live on the East Coast. And let's continue then to just talk about the humans with some good ideas and bad ideas are. So this was a thing at, and I haven't been there in years, at Sarasota Bay. I'm not even sure I'd be able to find it quickly. It's one of these down here. Anyway, what happened and what does happen is, okay, I built my beautiful house on the beach here, and I noticed that the beach is eroding, and it's like, well, yeah, that's what beaches do. So we go and we chuck in a big seawall. But what happens is like you can throw off the balance and how these things all work, and if water's going to be slapping up against that, and especially if everybody decides to do that, because when you have a seawall, what happens is that a wave hits it, and the energy doesn't really get dissipated at all. It just gets reflected back out. So what they had happen in Sarasota was everybody was doing that, right? Everybody built a seawall, and it's kind of like one guy builds a seawall, the next guy builds a seawall, the next guy builds a seawall. Why isn't? Oh, there we go. Yeah, like in here it was. I did like this boat tour through their marine, their marine museum, and they talked about this. And then we look for manatees and stuff like that. But if one person builds a seawall, then the next person builds a seawall, then the next person builds a seawall, and so on and so on and so on. What happens now is that wave energy bounces off one, off another, off another, off another, and that increases generally like the energy within the whole entire system, within that bay, until the people that don't have one, all that soft sediment that's just sitting there was getting swept out and destroyed, and they were like losing like the little mangrove islands they had through here. I'm not sure I'm in exactly the right spot because it's been so long, but that's the premise. And then so much so eventually that the walls themselves can't get undermined if enough of that sediment goes away. So a smarter idea, and one that people are catching on to this, is to build structures that might absorb that energy a little bit more. So this is from like a Syracuse.com news article when they were building the detached breakwater in Oswego. When they were reinforcing that, they did it with these big things that look like jacks, like kids toys. You know what I mean? Jacks? I don't know. Giant concrete. These things weigh tons. Like you can fit like one or two of them on a truck. And then they put them on a big barge with a big crane, and they went out and they carefully dropped them along that seawall. I'm not sure it will look like much in Google Earth, though we could try. But the good idea there is that those, when the waves hit them, the energy will go like wrapping around and bounce around within those, and it dissipates the wave energy rather than just reflecting it. I don't know if it'll sharpen up much more than that, but can you see them? I mean, they're there, right? So there's the old seawall, and to absorb wave energy, they piled all those things around it, which is a wiser idea. So yeah, what do you think? And so the human impact things are going to come down to yes, there's changing sea level. Yes, there's increasing severity of storms. So what might a barrier island have done for us when it was a dune, a beach, a dune system, and all of that? And I can't say it was meant to be this way, right? These weren't designed. Oh, look at all of them there. There you go. A dune wasn't designed by anybody. It's a function of nature, right? But if we had a regular profile with protective dunes, the land back here actually becomes more stable. By flattening and occupying these, that could be the rougher scenario. And again, I know you guys can buy the house. You're just in college, you're growing up there, but it should be something that we understand as we continue to expand populations. I had this course in person, not online, during Superstorm Sandy, and we looked at some of the photos the next day. And I talked about this, and I got some angry emails from some folks saying, "Oh, that's where I live," and I get it, I understand, but that's the conundrum. Do we continue? Do we always do the rebuild, no matter what, or do we at some point figure out some way to understand this balance of dynamic environments along with what we would like to have for a real estate investment that lasts for lifetimes? That's the tough question, one that I don't have an answer to. But I appreciate you listening to me babble about it for a whole term here. Good job, everybody. We'll finish up this segment, get into the final, and I wish you well. All right. And one last time, I'll awkwardly find the stop button. There it is. Take care.